welcome back to I Teach You Science. We're doing some more cluster questions today, as you could see, for the Earth and Space Science curriculums. I would say as a great strategy for using these videos, you should, you can listen to me read through the question, but once I get to the question, pause the video, try to solve it, and then unpause the video and see me explain it and see if you get it right. That's definitely the way to do this. Don't just listen to me explain it because you're kind of wasting the review. So here we go. We have modeling Earth's interior for this one. It says base your answers to question 1 through 6 on the information below. So let's see what it says. It says, while other planets experience tectonic deformation in the form of volcanic activity. So tectonic deformation means things are being destroyed by volcanoes right there. Earth is the only planet currently known to exhibit active plate tectonics involving multiple plates. So the Earth is broken up into plates, okay? And we're the only planet that is known to have this. To gain a better understanding of Earth's interior, scientists have developed models by using seismic waves, rock samples, and lab experiments. These models assist scientists in the visualization of Earth's complex interior and crustal dynamics. So they're saying they use models to figure this out. Conditions within Earth's interior cause different substances to be found at different depths. The table below shows this. Okay, so it's pretty much saying these are the layers. It shows the depth range of those layers, and then it shows the substances located at those regions. Okay, great. Seems fine. All right, now this graph below shows some information about the velocity of seismic waves as waves travel through the Earth's interior. So velocity is the speed. So it's saying the speed based on this is changing. So you could see velocity right there. And here are our layers. So we have the crust being here. We have the upper mantle in that section here. So you can see the crust is very thin. Then you have the lower mantle, the outer core, and the inner core. It says VP represents compressional waves and VS represents shear waves. So this is compressional, shear, shear. So these are types of earthquake waves. So compressional waves can travel through solids, liquids, or gas, but when they do move through different material, they sort of change direction and change their speed. So for example, if a compressional wave all of a sudden hits a liquid or a different substance, it's going to change speed. It might slow down. A shear wave here is another earthquake wave. These can only travel through solids. So when it hits a liquid, it gets absorbed and pretty much like disappears, essentially. It gets absorbed. So knowing that, we could see that the outer core, it seems like, has no shear waves. The lower mantle has some, and the inner core has some. But the outer core does not have any, which means the outer core is actually a liquid. So let's see what this says. Which row in the table below correctly describes the substances found in the interior and the characteristic of that interior layer of the Earth? So it wants us to use both of these charts to figure this out. So what I'm going to do is I'm going to label which substances are which layer. So the way I'm going to do this, I'm going to say, okay, liquid iron, right? I'm going to go up to this chart. I'm going to see, okay, find it. There's liquid iron. So I know that since there's liquid iron, I'm referring to the outer core. So I'm going to come down here and I'm going to write outer core. So now I know that that's what A is talking about. I'm going to do this for all four. So solid stable iron. So let's go up here. Solid stable iron. So that means that's the inner core. I'm going to come back down here. I'm going to write this. And this is how you should do it when you take the test, right? Inner core. You should write as much. You can see all my little notes here. You're going to have to do that because this is way too much material to make any sense of it if you don't start writing little notes to yourself. Pyroxene and quartz, where are they? So pyroxene is here, but quartz is here. So this could be the upper mantle or the crust. I don't know. It says it could be either one right now. So upper mantle or the crust could be either one. I'll just write what we know. And then magnesium silicates Let's see where those are. Magnesium silicates, lower mantle. Okay, so now we got our zones. So now really I don't need that top chart anymore. Lower mantle, okay. So now we got to match this layer with the characteristic, and this characteristic in here is going to be given to us on this chart here. So I'm going to say, okay, in the outer core, is that found in a layer where compressional velocity is greatest? So let's see, outer core. You could see compressional velocities here, this line, that's about, at its highest, it's about, I don't know, 10.5 kilometers per second, but that's not the highest in all of them, right? There's more compressional velocity here and here. So that statement is wrong. So it's not this. Okay, now we're going to go inner core. Is that found in a layer where the compressional wave velocity is approximately 11.2? So let's go see that in the inner core. So compressional waves VP, is that about 11.2? Yes. So this is a contender for the right answer, but we're going to check the other two just to be sure, because if we do see something true in CRD, then we know we could have messed up on B, because obviously there's going to be only one right answer, right? All right, let's see. Upper mantle or the crust. Is this found only at a depth of 500 kilometers? So upper mantle right here, that goes down to almost 1,000. So it's pretty much from 0 to 1,000. So this cannot be true. So this one's wrong, which is a good sign that B's right. So let's do the last one. Lower mantle, found in a layer where shear wave velocity is greater than compressional wave velocity. So automatically I could see in no layer is the shear velocity higher than the compressional velocity. It's always the compressional is higher. So that is wrong in this section here, which means we have 2 as our answer. All right, number 2. Seismic wave information was used by scientists to infer the depth of the Earth's interior layers. So we're saying the wave information is used to measure the depth. So that's how deep the layers are. And the states of matter found of these layers. States of matter, so that's going to be like solid, liquid, or gas. For each piece of evidence below, place an X in the appropriate box to indicate the characteristic that can be inferred and explain how this evidence changes and is used to determine this characteristic. Okay, so it's saying if there's a sudden change in velocity, what could that mean? Is there a change in density of the material or a change in magnetism? So the sudden change of velocity, as we said, has to do with the wave going from a solid to a liquid to a gas. So the difference between a solid, liquid, and a gas is the density. So this is going to be this. And for our explanation, we could say, as seismic waves travel through different density material, we could say like solid to liquid, it changes speed. All right, let's see the next one. Presence of certain types of seismic waves. So we did say a shear wave cannot go through a liquid. So that means that the state of matter is going to be what we can find out. So state of matter, and we could say shear waves cannot travel through liquid. That's all we need to say. Now, what I'm going to do as I go through this, I decided I'm going to rate the difficulty of these questions, in my opinion, from 1 to 10. I would say this chart question here, I'm going to give that a solid 7 out of 10, 10 being really hard. Not that it's really hard, but to be able to go back and forth between those two charts like I did, that requires some serious effort. So I'd say that's pretty hard. This one, you do have to have content knowledge of how compressional and shear waves work, but if you knew that, then this is not hard. So I would say this is like a 4 out of 10. All right, we'll keep going. We'll see if we hit any 10s. All right, here we go. Tectonic processes are responsible for the formation of many types of rocks and minerals found on the Earth. The model below shows some information about different tectonic plate interactions found on and below the Earth's surface. Okay, so we have a lot of plate action going on here. Subduction, all sorts of stuff. All models of Earth's interior depend on indirect evidence. These models predict the sources of the heat in the Earth's interior. The substances found in the different layers of the Earth's interior determine the possible source of heat in the layer. The core contains elements that like to be with iron, but the mantle and crust contain rock-loving elements. These elements are the source of rock-forming minerals in the Earth's crust. Uranium, thorium, and potassium are unstable isotopes that are examples of these rock-loving elements. So I'm going to underline this because I know when I start seeing the word unstable isotopes, it has something to do with radioactive decay, which is a page on the ESSRT. So I might be able to use that, but we'll see where this is going. This is a lot of wordage here. Which statement correctly describes a source of heat within the Earth's interior? Okay, so let's start. So see, radioactive isotopes. Okay. In the Earth's interior, decay in the mantle and crust, further driving convection currents. Okay. Here's what we have to know here. Convection currents are in the mantle, generally. So convection currents happen in, they pretty much need to happen in a semi-liquid or a gas. So they cannot happen in solids. Cannot. So that I need to know that for this. Cannot happen in solids. So since they're saying convection currents happening are in the crust, for number one, say in the crust, this is wrong. So one's out. Number two, radioactive decay in the mantle, radioactive activity in the mantle and crust helps to cycle materials into the Earth's inner core and asthenosphere. Okay. Heat is going to, if you have the Earth, heat is radiating out generally of the inner core. Heat's not really going to be going back into it from radioactive decay. I mean, maybe a little bit. The asthenosphere is a possible answer here. So this is not totally wrong. It's weird, but not totally wrong. So we're going to just not cross that one out. Radioactive elements in the Earth's interior decay, cycling materials and convection currents only within the crust. This is totally wrong. Because first of all, it happens, like we said, in the mantle. And it can't happen. It's not really happening in the crust. So that's out. Radioactive isotopes in Earth's interior decay, cycling materials in convection currents formed in the mantle and asthenosphere. Okay, that's huge. That is where convection currents really occur, in the asthenosphere. So this is pretty much going to be right because we have the mantle and asthenosphere. This one that we didn't cross out has the inner core and asthenosphere. So number 4 is going to be our best bet. So I would say that question's maybe like, I don't know, because really people might get it as a 50-50 between 2 and 4 since they saw asthenosphere. So I'd rate this one like a 5 out of 10 because you would have to know convection currents are in the mantle and asthenosphere. That's the content there. And plus, this is really wordy, honestly. So like this quote stuff, it's kind of weird. All right, let's see what's next. The model below represents processes involving rock formation. We got tectonic processes labeled A and B that are missing. So let's look for them. So this is the rock cycle. Great. So here's tectonic process A and then tectonic interaction B. Using evidence from the Earth's surface and interior model, complete the rock cycle model by identifying one plate interaction that's responsible for the formation of each rock type indicated. So this is saying for A, I have to make a metamorphic rock because see the arrow's pointing to metamorphic. And for B, I have to make an igneous rock. So I need to know which plate boundaries are responsible for making those two types of rock. So this is like pure content. So for this, I need to know that so I want to make metamorphic rock, right? Metamorphic rocks are found in areas with a lot of pressure. If you want to go for a tectonic plate that is going to make a lot of metamorphic rocks, the best answer is going to be some sort of mountain building. To make a mountain, you need to do convergent with 2 continental plates. That would be your best bet. And then for igneous rocks are formed from magma, the cooling and solidification of magma. You're going to find magma at rift valleys, at divergent plate boundaries. So this is going to be like divergent at like a mid-ocean ridge. So I would say, honestly, if you knew the content of this question's super easy. That's a 2 out of 10. All right, let's go. We're crushing this. Certain magnetic minerals and rocks can record the direction and intensity of Earth's magnetic field at the time they are formed. The direction of Earth's magnetic field has reversed several times during Earth's history. These reversals are recorded in the bedrock at the ocean floor. The model below shows some information about the age and magnetic polarity of the ocean floor along the Juan de Fuca ridge system. Okay, so we have the Juan de Fuca ridge. A ridge is at a divergent plate boundary. So essentially, if this is the ridge right here, this plate's moving this way and this plate's moving this way. So all the magma is coming up here. This is where the new magma is coming up out of the Earth. And then it moves symmetrically up to the northwest and southeast. So they're saying the magnetic polarity are normal or reversed here. And you could see it's like a mirror image. So for example, like this is all normal next to the ridge right here. And then the pattern's going to continue up and to the left and down and to the right. So it's like a mirror image. So if I were to put like just an X pretty much here, a location that's here is probably going to be about the same age as a location over here. So because they're equidistant away from, and actually, I don't know where that X would be. It would be like over here maybe. Equidistantly the same age. So areas near the right here are going to be about the same age as the area there. So looking at A and B, before I even look at the question, A is younger rock and B would be older rock because B is further from the rift, right? A was just spawned in recently from the new magma. So that's what we got from this. We don't even know what the question is, so let's see. Which statement correctly compares locations on the Juan de Fuca ridge model? So yeah, this was predictable, right? So number one, the basalt at location A is older than basalt at B. So we just established that that's not true. So this is wrong. A greater amount of outward flow of energy, so outward flow of energy from the interior of the Earth occurs at A than B. So A is at the rift, closer to the rift. So yeah, I mean, that's going to be spewing out more energy from the interior of the Earth because that's where like the new magma is coming up. So that could be true. Number three, the magnetic polarity of basalt at A is the same at B. So this is on the dark area and it says that would be normal. And this is on the white area and that says that would be reversed. So that's wrong. The motion of the plate is from B to A. So it's saying from B to A. Now that's wrong because this is a rift valley, so these are separating. But if you didn't know that, we might be able to get some information from our reference table. So if we go to our tectonics here and we try to find the Juan de Fuca plate. So it's saying right here, this sort of pattern here is diverging. So yeah, so we could say that these are definitely going apart. And then there's converging happening on the right side, but that's not where this plate is in our picture. So that could help you a little bit that it's diverging. So that's wrong. So it's 2. I would say that's kind of hard. There was a lot of content in that because you definitely have to know how a rift valley works with the older, further away. But then it was just kind of reading the chart. I don't know. Like, that was fine. I would say it's pretty fine. So let's give that a 5. So far, that first graph question I have is the hardest one. Okay. Describe how the pattern of magnetic field reversal of the ocean floor basalt is... The ocean floor basalt shown in the rocks on either side of the ridge is evidence for convection currents. Okay, well, pretty much when you have a divergent plate, this is content again. So if the magma is coming up here, it's moving this way, right? Because the convection currents below it are going like that. So if the convection loop's going to the left on the left plate and the right on the right plate, the plates are going to separate, and then the magnetic polarity is going to be mirrored like normal, normal, reverse, reverse on both sides. So since there's a mirror image happening and the plates are moving in opposite direction, we can conclude that the convection currents are moving underneath it in that way. So I just got to word that in a certain way. Describe how the pattern of reversal shown is evidence for convection currents. Okay, so we could be like, since the pattern of fields is mirrored, the plates are separating. This is evidence that convection is moving them underneath in the mantle. That's really all I'm going to leave it at. Sorry about my bad handwriting on this. So I don't know. That's fine. That's a 5 out of 10. There was, so far, I mean, there was only really one, like, easy question, right? And there was, like, one a hard one. The rest were, like, middle of the road. All right, so I think that's good enough for this cluster. If you like this series, like I said, leave a comment. I will keep making these cluster videos, and we'll keep practicing together. I hope this is useful for you, and good luck in your studying. See you on the next one.